Gold is one of the least reactive metals, but under the right conditions it moves through Earth's crust. In hydrothermal fluids, gold dissolves as chloride or bisulfide complexes. These fluids carry only 1 to 10 parts per billion of gold, yet move it for kilometers. When temperature or pressure drops, gold precipitates, often with quartz and sulfide minerals. This process forms veins, disseminations, and stockworks with grades from grams to ounces per ton. Gold's solubility shows how tiny chemical shifts can generate entire ore bodies, the engine behind most of the world's gold. Some of the richest gold zones aren't deep underground. They form when nature enriches deposits near the surface. Hypogene deposits form first, deep underground at high temperatures and pressures. Later, weathering and oxidation create supergene blankets just below the surface. Gold grades in supergene zones can increase by 2 to 10 times compared to the original ore. A classic example is Chile's Chuquicamata deposit, where weathering concentrated copper and gold into rich supergene caps. Always check oxidized zones at the surface. They may be the key to finding richer ore hidden below. Gold is not distributed randomly. It follows structures that control where deposits form. Faults and shear zones act as highways, allowing hydrothermal fluids to carry gold for kilometers. Folds can also trap fluids, concentrating gold along hinges and limb contacts. Breccias and shattered rocks create open space for quartz veins and sulfides to precipitate. Famous belts like Canada's Abitibi and Australia's Yilgarn host world-class deposits along these structural corridors. When exploring, always map structures first. They're the framework that controls where gold concentrates. Gold deposits are surrounded by alteration halos, chemical changes from hot fluids. These halos are footprints that point prospectors toward hidden ore. A key indicator is sericite alteration, where feldspar breaks down into fine white mica. Bleached rock or silky mica means you're close to hydrothermal activity. Chlorite alteration turns rocks green. These halos form at lower temperatures, farther from the ore, grading inward toward hotter zones. Carbonate alteration is another sign, where calcite and anchorite replace host rocks around veins, revealing fluid chemistry changes. These halos form concentric shells based on temperature. Green chlorite forms at the cooler edges, then carbonates with high-temperature sericite closest to the vein. This zoning maps the pathway of ore-forming fluids. Geologists use halos to vector toward deposits, sampling across zones to trace geochemical gradients back to the source. Even subtle halos can point the way. For example, in Western Australia, sericite halos surround gold-bearing veins, while in Nevada, carbonate alteration marks major deposits. For prospectors, these halos are key visual clues. Discoloration, bleaching, and green zones are all hints that valuable ore may be nearby. Some of the richest gold zones aren't deep underground. They form when nature enriches deposits near the surface. Hypogene deposits form first, deep underground at high temperatures and pressures. Later, weathering and oxidation create supergene blankets just below the surface. Gold grades in supergene zones can increase by 2 to 10 times compared to the original ore. A classic example is Chile's Chuquicamata deposit, where weathering concentrated copper and gold into rich supergene caps. Always check oxidized zones at the surface. They may be the key to finding richer ore hidden below. Arsenic is one of the most reliable pathfinders for gold, often leading directly to hidden deposits. The mineral arsenopyrite forms when hot fluids interact with host rocks, locking in tiny amounts of gold. In Carlin-type deposits, gold values rise sharply when arsenic exceeds 1,000 parts per million. These halos can stretch hundreds of meters, giving geologists a larger target to drill. By testing rocks and soils for arsenic, explorers can trace the chemical footprint back to the gold source. Arsenic doesn't just accompany gold, it points the way. Some of the best gold pathfinders aren't the obvious ones. Antimony, bismuth, and tellurium often reveal the hidden footprints of gold systems. Antimony halos outline epithermal veins. Bismuth tracks orogenic and intrusion-related deposits. And tellurium forms tellurides, key in historic gold rushes like Cripple Creek. Together, these minor elements can expand the search radius beyond visible gold, making them essential tools in modern exploration. Antimony, bismuth, and tellurium, small elements, big clues. If you spot mercury in the ground, you might just be hot on the trail for gold. Sounds strange, let me explain. Mercury may seem like an odd sidekick for gold, but in epithermal gold exploration, it's one of the best clues around. When hot fluids rise underground, mercury vaporizes and spreads out, leaving chemical halos in soils and clays, sometimes hundreds of meters from the real gold. These mercury anomalies show up way before gold does, giving geologists an early heads up that precious metals could be hiding below. So, next time you hear about mercury, remember it's not the treasure, but it might just lead you to it. Stop looking for gold directly. Look for the rocks that hide it. Magnetics makes finding secret gold deposits way easier. Here's the trick. Magnetic surveys measure tiny changes in Earth's magnetic field. Gold itself won't show up, but the rocks that often host gold, like magnetite-rich zones, light up like a beacon. In greenstone belts, magnetic highs can point to mafic intrusions. Faults, places where gold loves to hide. With aeromagnetic surveys and a dash of geochemistry, explorers can spot gold targets even if they're buried deep. Fast, affordable, wide-reaching. Magnetics is the pros' first move in modern gold exploration. Gold deposits often occur with sulfides, and that's where resistivity and induced polarization, IP, become powerful tools. Resistivity measures how easily the ground conducts electricity, while IP detects how charges build up in minerals. Sulfides like pyrite and arsenopyrite create strong IP responses, and zones of clay alteration can lower resistivity. Together, these methods map subsurface targets where gold is likely to occur, even beneath soil or cover. By combining resistivity and IP with magnetics and geochemistry, explorers can pinpoint drill targets more effectively and reduce exploration risk. Satellite spectral imaging is revolutionizing gold exploration. Tools like ASTER and Landsat detect subtle differences in surface minerals by measuring reflected light across multiple wavelengths. Hydrothermal alteration zones, rich in clays like kaolinite, sericite, and chlorite, create distinct spectral signatures that stand out against unaltered rock. These alteration halos often point directly toward buried gold systems. Unlike soil sampling or ground geophysics, spectral imaging covers vast areas quickly, guiding geologists to priority targets before stepping foot in the field. By combining spectral data with mapping and geochemistry, explorers create a powerful roadmap for discovery. Spectral imaging, seeing gold clues from space. I bet you didn't know geologists can sniff out gold without ever striking rock. It all starts with a handful of soil and some serious science. When geologists hunt for gold, they collect soil samples to detect tiny traces of gold and other clue elements. Most soil, it's just background less than 2 parts per billion of gold. But if a sample jumps above 5 parts per billion or 10 parts per billion, that's a red flag there might be gold lurking below. By mapping these hotspots across a grid, explorers can outline underground gold zones before drilling a single hole. It's low-cost, high-reward, and it's helped uncover gold deposits all over the world. I will never look at gold hunting the same way after learning this. It's not just about the gold, it's about the clues hiding all around it. Geologists use geochemical ratios like gold to arsenic or gold to silver to crack the code of hidden deposits. For example, a high gold to arsenic ratio often points to Carlin-type systems where gold is locked in arsenopyrite and almost impossible to see. Meanwhile, comparing gold to silver can separate epithermal from orogenic deposits. If you see more silver, you might be looking at a shallow, low sulfidation environment. These ratios are like geological fingerprints, helping explorers decide, is this a world-class ore body or just background noise? In gold exploration, it's not just the elements. It's the relationships between them that reveal the treasure. Geology is full of secrets, and ore microscopy unlocks them. Ore microscopy is like detective work for rocks. Geologists study polished slices under reflected light, hunting for tiny flecks of gold trapped inside minerals like pyrite. These textures, overgrowths, replacements, intergrowths, tell us how the gold formed, moved, and where it hid. It's not just about spotting gold, but understanding its story, how it got there and how to get it out. In less than a millimeter, Ore microscopy bridges exploration with extraction, guiding everything from deposit models to the best ways to recover that hidden gold. Not all gold comes from gold mines. Huge amounts are recovered as a byproduct of copper porphyry deposits. At Grasberg in Indonesia and Bingham Canyon in Utah, copper is the primary target, but the gold output alone ranks among the world's largest producers. In fact, byproduct operations supply millions of ounces every year, often at very low cost since the copper pays for the mining. This hidden source means global gold supply is tied closely to the copper market. Byproduct gold proves that sometimes the world's biggest gold mines aren't gold mines at all. Did you know a century ago, gold mines averaged 10 times more gold per ton than today? So what happened? Let's dig in. In the early 1900s, gold mines commonly found over 10 grams per ton. By the 1950s, that number had halved. Fast forward to now, most big mines are chasing just around 1 gram per ton. Why the drop? The richest, easiest gold is already gone. What's left is deeper, lower grade, and harder to process. Modern technology helps, but mining today is about moving mountains, literally, just to find those flecks of gold. Ore grades are down, costs are up, and gold mining will never be the same. Gold doesn't settle everywhere. It concentrates in natural traps. Because it's so dense, gold drops out where water slows down. Look behind boulders, inside cracks and crevices in bedrock, or along the inside bends of streams where current loses energy. False bedrock layers like clay or hardpan also catch and hold gold, keeping it from sinking deeper. Drop pools at the base of waterfalls or riffles in riverbeds often hold pay streaks, where flakes and nuggets concentrate together. If you want to find placer gold, always look where the river's energy changes. That's where nature hides its treasure. You need to hear this if you're a gold prospector. Finding gold isn't random. It's all about gravity. Here's how hydraulic sorting works. Gold is nearly 19 times denser than water, way heavier than sand quartz magnetite. When water rushes through a creek, it picks up lighter sands and carries them away downstream. But gold, it's so heavy it drops quickly, settling in cracks behind rocks deep in natural riffles. Black sand, usually magnetite ilmenite, often tags along, but gold always sinks deeper, sometimes all the way to false bedrock. So next time you're out prospecting, remember, gravity is nature's gold sorter. That's where you should be looking. Glaciers act like giant conveyor belts for gold. As they grind across mountains, they pick up bedrock fragments containing gold, then drag them for kilometers. When the ice melts, that gold gets released into tills, outwash plains and stream systems. In some regions, nuggets have been carried more than 100 kilometers from their original source. Prospectors study glacial flow patterns, moraines, and drumlins to trace this transport back toward undiscovered bedrock deposits. Glacial gold isn't random. It's the product of ice reshaping entire landscapes and scattering ore far beyond its source. Desert placers. Not all placer gold comes from rivers. Deserts have their own hidden deposits. In arid regions, flash floods act like short-lived rivers, washing gold downhill and trapping it in dry washes. Wind also plays a role, concentrating lighter sands and leaving behind heavy black sands mixed with gold. Prospectors search in natural traps like caliche layers, desert pavements, and dry gulches where water once flowed. Metal detectors are especially effective in deserts, picking up nuggets missed by earlier miners. Desert placers remind us that even without constant water, gravity still works, and gold still finds a way to concentrate. Ever wondered where the world's gold really comes from? Let's dig into the biggest players. Indonesia's Grasberg mine is a giant, pulling up millions of ounces of gold and copper every year. In Uzbekistan, Maruntau stretches out nearly 2 miles across, making it the largest open-pit gold mine on the planet. And in Nevada, the Carlin Trend isn't just one mine. It's a whole cluster, together producing over 90 million ounces in their lifetime. But here's the catch. These megamines work at huge scale, but often with gold grades close to just 1 gram per ton. Still, their massive output keeps the world's gold supply flowing and proves, in gold mining, volume is king. Gold mining doesn't have to mean dangerous chemicals forever. For over 100 years, cyanide's been the go-to for pulling gold out of rock. It's fast, efficient, and risky. Accidental spills can threaten water, wildlife, and communities. That's why scientists are searching for safer ways to recover gold. Thiosulfate is showing big promise, especially with tough ores. Glycine leaching is gentle and low toxicity. Chloride is being tested in the lab. Bromine is being tested in the lab. Right now, cyanide still dominates. But as mining companies aim for cleaner and greener operations, these alternatives could shape the future of gold. Because getting the gold shouldn't cost the planet. If you think gold just means riches, think again. Sometimes the real price is paid by rivers. Sometimes the real price is paid by people. Here's why. In California, miners once used mercury to extract gold, leaving behind toxic rivers, contaminated fish, even today. Fast forward to Romania, 2000, a massive cyanide spill at Baia Mare poisoned waterways across Eastern Europe, killing fish, threatening drinking water. These disasters show gold's dark side, environmental damage that lingers for generations. Modern mines now use stricter rules and better tech, but the lesson's clear. Every ounce of gold leaves a footprint. So the next time you see something shiny, remember, responsible mining isn't just good business, it's vital for our planet. Am I the only one who didn't realize America's gold rushes were this huge? Grab your pickaxe, we're going mining. In California's legendary Mother Lode, miners pulled more than 30 million ounces of gold from the earth. But South Dakota's Homestake mine topped that. Over 40 million ounces mined across a full century, making it America's longest-running gold mine. Then Nevada took the crown with the Carlin Trend, over 90 million ounces and counting. Each gold camp tells a story. Wild placer beginnings, gritty underground innovation, today's massive open pits. It's a legacy of discovery, technology, and pure persistence, turning local rushes into world-class mining legends. If you're a fan of gold rush legends, buckle up. The Klondike placers rewrote history in remote Yukon. The California placers rewrote history across the Sierra, but their stories are wildly different. In California's Mother Lode, rich placers burned out fast, averaging about half an ounce per ton. But in Canada's Klondike, nuggets were bigger and grades insane. Some creeks averaged 2 ounces per cubic yard. California's rush fueled new technology and mass migration westward. The Klondike proved permafrost is a gold trap that works for thousands of years. Both camps changed history, but the geology, that's what set them apart.